Hello and welcome. How's everyone doing? Good? All right. Before we get started, I just want to ask a few quick questions, just to set the context a little bit. How many of us here in the room have used Amazon S3? Yes, that's everyone. It's amazing. How many of us have used Amazon S3 for machine learning use cases? All righty. That's a good number. And last question before we move on. How many of us have tried to optimize storage performance for machine learning use cases? Not specifically in the context of S3, but storage performance in general. All right. So the good news is, with the launches we're going to talk about today, you don't have to work on optimizing storage access for ML use cases with S3. These features will do that work for you. Isn't that exciting? All right, so on that note, let me just get started. My name is Devbrat Kumar. I'm a product manager on the Amazon S3 team. And today, I and my colleague James and Alex are going to talk to you about how you can use these new features that we announced recently to optimize performance for machine learning training on Amazon S3. We are first going to talk about why run machine learning training on Amazon S3. Then we are going to talk about how you can run ML training on Amazon S3, regardless of whether you are running in a fully managed setting and training on Amazon S3 using our purpose-built services like Amazon Sagemaker, or you are running your self-managed infrastructure and services, and you are looking for general-purpose solutions. We'll cover all of the best practices and recommendations in the talk today. And finally, we'll summarize the key takeaways and conclude our session. So the first question, I guess, that comes to our mind is, why run ML training on Amazon S3? Well, machine learning, as we know, begins with data. And Amazon S3 is the best place to store your data because of its unlimited scalability, its high elastic throughput performance, and high durability. Customers of all sizes and industries use Amazon S3 to store and protect petabytes of data for use cases such as data lakes, media and entertainment, Internet of Things, genomics, healthcare, life sciences, so on and so forth. When you have all of this data already in Amazon S3, then you would think it's the natural place to start your machine learning journey from. Well, that's absolutely true. There are some very sound and specific reasons why you should use Amazon S3 as the foundational storage for your ML machine learning artifacts and training data. First, Amazon S3 offers a range of storage classes you can choose from based on the data access patterns, the cost requirements, and the data resiliency requirements of your workload. For example, you have S3 Intelligent Tiering that automatically optimizes storage costs for you. It is one of the most popular storage classes that we have in Amazon S3 that customers use for use cases like machine learning and data lakes. That's because the access patterns are often unknown, and S3 Intelligent Tiering, for a small monitoring and automation charge, moves objects that have not been accessed to lower cost tiers, delivering cost savings to you without any impact on performance and without any operational overheads. Additionally, Amazon S3 also provides features to optimize costs throughout the lifecycle of your data. For example, once you set lifecycle policies on your bucket, then the data moves to other storage classes, delivering cost savings to you without requiring you to do any change in your application. So to summarize this point, with our range of storage classes and cost optimization features, you can store terabytes to petabytes of data on Amazon S3 and benefit from these features to get automatic cost savings. Second, Amazon S3 delivers very high aggregate throughput that is extremely important for machine learning training specifically, because you want to get your data as soon as possible from Amazon S3 to your compute instance. Recently, we have announced, I would say over the last few days and over the last few months this year, we have announced a bunch of optimizations on the client side, including a brand new file client for Amazon S3 called Mountpoint, integrations of AWS Common Runtime Library, which does automatic performance optimizations for you in AWS SDKs like the Boto3 or the Python SDKs, and also a new S3 connector for PyTorch. With these new client integrations, you get high data transfer rates between your Amazon S3 bucket and your machine learning job. And the key message here is that these clients do things like request parallelization, manage retries and timeouts, so that you don't have to write any code for optimizing storage access, as I was saying, for ML use cases. Last but not the least, actually, it's a very significant point. Besides these client-side optimizations, we also announced a brand new storage class yesterday. It is called S3 Express One Zone. S3 Express One Zone is a new storage class that is purpose-built for delivering low-latency access for performance-oriented or performance-heavy workloads. It's specifically useful for latency-sensitive workloads, for example, for training jobs where you have a lot of random data access happening. What we have heard from customers is that in use cases such as training vision models, there's a lot of random data access that happens, which my colleagues will dive deeper into, and these workloads happen to be latency bound. So with Amazon S3 Express One Zone and its integration with AWS SDKs as well as Mountpoint for Amazon S3, you can achieve low latency as low as low single-digit millisecond first byte latency, so that your latency-bound workloads finish fast and you save on compute costs. Finally, Amazon S3 integrates with a number of our purpose-built services that help you run different stages of the ML lifecycle. Amazon S3 integrates with Amazon Sagemaker so that you can build, train, and deploy your machine learning jobs in a fully managed setting. It also integrates with Amazon Bedrock so that you can use popular ML models that are available from top companies and then fine-tune them and customize them using your data in S3 buckets. If you're running in a self-managed setting, then you can also use Amazon EMR to run data preparation jobs, for example, image augmentation at scale. And if your applications need a fully featured file system interface, for example, to collaboratively facilitate collaborative editing of data, then you can use Amazon FSx for Lustre, which integrates seamlessly with Amazon S3, giving you a fully featured file system to work with for applications that are file-based. So to summarize, with Amazon S3's range of storage classes and cost optimization features, the new high-performance storage class, the S3 Express One Zone, our new client integrations that we launched over the last few weeks, I would say, and its seamless integration with purpose-built services, you can use Amazon S3 as the foundational storage for all your machine learning needs and build your workflow on top of it. Due to this reason, customers are running ML jobs of all sizes on Amazon S3 and benefiting specifically for training very large models that they can use, that they train working with Amazon SageMaker, for example. One of the good examples that we have in this respect is that of the Technology Innovation Institute, or TII, that built their Falcon series of models using Amazon S3 and Amazon SageMaker. It is one of the most popular models on the Hugging Face leaderboard today, and it was built with 180 billion parameters trained on 3.5 trillion token data set. It was built on a cluster of hundreds of MLP4D24X instances, benefiting from S3's elastic throughput, using S3's integration with, say, over Boto3 or the Python SDK. So basically, this is a good example where the customer used the elastic throughput of S3 to build a very large-scale model, which happens to be one of the most popular models on the leaderboards, as I mentioned. While Amazon S3 is really useful for large-scale models, the performance optimizations that we talked about and which my colleagues will dive deeper into are relevant for essentially working with ML use cases at any scale. And they're applicable regardless of the data set size and the size of the ML model you are working with. So to dive deeper on that and take you through the full ML lifecycle, I'll invite my colleague, Alex. Thanks.
Thank you, Tim. Good morning. My name is Alexander Arzhanov, and I'm Specialist Solution Architect here at AWS, helping our customers to deploy and optimize machine learning workloads on the cloud. And in the past 3 years that I've been here at AWS, I've talked to different customers in different use cases, but every single machine learning project usually follows the same cyclical pattern. So where everything starts with data ingestion, data exploration, and data preparation. And then in the building phase, data science team will usually take different or test different approaches, test different machine learning algorithms, and once they are satisfied with the approach, they will go and train those end-to-end on an entire data set that was previously preprocessed until convergence. And of course, they will monitor different metrics that make sense for the business use case they solve. And once they're satisfied with the performance, those models will be deployed out to the production. And there, the models themselves will be continuously monitored. So if the performance degrades, the machine learning lifecycle will repeat itself. However, it is important to understand that throughout those different stages in the machine learning lifecycle, your data lives and it continuously evolves on Amazon S3. So, for example, if we take the case that Dev has previously talked about, TII and the Falcon models, in the pre-training of large language models, what you might start here in this case is that you have some kind of scrape of the entire internet with petabytes of unstructured data, HTML files, so different media file formats stored on Amazon S3. And then your data science team will work around the clock in order to deduplicate this data, filter, clean it, so that at the end, what you end up having is some kind of more structured, high-quality data set that you store back to S3, and it can be Parquet files or different other machine learning specific formats. And then those terabytes of data will be continuously streamed into the compute cluster, and the training phase itself may go for days, weeks, or even months. And of course, throughout the training, the snapshots of the model weights will be taken periodically. In case of large language models, they can be, again, hundreds of terabytes in size and put back on Amazon S3. To summarize here, if you're doing machine learning on AWS, it is really important to understand where, how, in which data format to store your data in order to optimize for performance and cost. So regardless also of different machine learning frameworks or machine learning tools that you might be using, it is really important to understand the implications of the proper data I/O performance. So, for example, if we take the training phase, we can see why this is important in this case. So, if you have the data I/O performance, if it is suboptimal for the training phase, what you end up is you end up with your compute resources that are underutilized throughout the training. And it is something that you don't want to be doing, because probably the most expensive resources, being the GPUs and the other accelerated compute instances, they will be end up idling throughout significant amount of time during the training. And also somewhat connected to this is the bottleneck which you have in your training, in your data I/O, will you will end up having your machine learning training runs to take longer to finish, and this will, of course, slow you and your teammates down in iterating throughout this machine learning lifecycle. Okay, so performance is really important, but which main considerations should you have in your mind when you talk about this topic? So first of all, naturally, it is the total amount of data that you have, the total data set size, and the number of files that your data set has. Naturally, if your data set is large, it will take longer to download this data set, or even list files in some cases. Somewhat connected to this question is the question of how your data set is composition. So if it is comprised of large number of small files, or have you previously serialized your data set so you have just a few larger chunks? Another question that you might be asking yourself is whether you need to download this data upfront to your local instance storage, or would you rather have this data set streamed on demand as your training script demands the data. And finally, one of the important questions that I usually challenge my customers with is whether you truly need to have fully random access during your training to the training samples, or can you still design your training algorithm and your data loader to consume training samples one by one sequentially. So let's double down on this last topic because it is really important. So sequential reads versus random reads. I usually start this conversation with my customers by drawing the analogy to the good old hard disk drives that you almost all are certainly familiar with. So if you remember, the hard disk drives have this mechanical actuator arm that moves around the spinning disk plater and reads different memory blocks. So in this case, we have sequential reads if our memory blocks are read contiguously one after another so that the mechanical arm doesn't have to move around much. We have random access pattern. If we start requesting data at random, that means that our mechanical arm will have to move all around the disk plater in order to read those memory blocks. And this will incur some delays when reading subsequent memory blocks. So the situation in the context of machine learning workloads is somewhat similar. So again, by the analogy to the HDDs, we say that we have sequential read patterns in our machine learning workflow if our data set is comprised of small number of large files, and each file contains many, many training samples, so that you can quickly read each training sample contiguously one after another only by firing one single GET request. We say that we have a random access pattern in our machine learning workload if our data set is comprised of large number of small files and each file represents just single training sample. In this case, we end up firing GET requests for every single training sample. Alternatively, we can still have a situation where we have serialized our data set into smaller number of larger files, but our data loader requests data from different parts within this file. For example, by firing a byte range GET request to S3. In either of those cases, what we end up doing is we end up firing many S3 GET requests in order to read the same amount of data. So let's illustrate the performance implications for these two read patterns with these two fictional calculations. So first, let's say that we have a computer vision task at hand. We have our data set comprised of JPEG files, let's say. And in the sequential read case, we have first serialized this data set into larger file chunks. Maybe we're using protobufers for this, and place those as objects on Amazon S3. And let's say that every object is about 150 megabytes in size. And then we start our data loader with a single thread. So we start getting data from the S3 by firing the GET request. But actually, until we get the first byte back, it takes some time. And this time is usually called as time to first byte latency. But after we have gotten this first byte back, we start downloading our data samples in bulk, and let's say it takes only 1 second to do so. If we assume that our time to first byte latency is approximately, let's say, 100 milliseconds, we arrive to the conclusion that we have an effective throughput, in this case, of about 140 megabytes a second. And of course, I must add here, this is a fictional scenario where you have only single client thread. Amazon S3 on the server side can scale naturally to much larger numbers. Continuing with our fictional example of single client thread, now we have the random access pattern where our data set is stored as raw JPEG files on Amazon S3, and each JPEG file represents single training sample. So we, again, start firing GET requests, and every time we fire a GET request, we have to wait TTFB amount of time. And then, let's say in this case, that our download time for those tiny files is negligibly small compared to the time to first byte latencies, and can be neglected altogether in our quick calculation here. In this case, we quickly arrive to the conclusion that our throughput will be about 140 times lower than in the sequential case. But of course, it is quite unlikely that you build a data loader and read data with just a single thread. Nonetheless, it was very illustrative to show the drastic differences in these two different read patterns. On the server side, however, as I have already mentioned, Amazon S3 can scale to much larger throughput numbers if you parallelize your calls properly. However, when you start parallelizing your calls on the client side, you also increase the strain on the CPU resources. And it is still recommended, if you're trying to optimize for the throughput, to follow the sequential read pattern. Despite this, there might be still situations where you don't want to serialize your data sets, or you just can't do this because of the peculiarities of your machine learning algorithm, but still would like to stream data from Amazon S3 with high throughput. So as Dev has mentioned previously, yesterday we have introduced our new Amazon S3 storage class, S3 Express One Zone, which is purpose-built to deliver consistently single-digit millisecond latencies. And it is also the first storage class of Amazon S3 that allows you to select an availability zone. And by doing this, you can collocate your compute and storage resources in order to optimize for throughput and the cost. And in one of the benchmarks that we have performed, we have seen that Amazon S3 Express One Zone can deliver time to first byte latencies that are 10 times lower than in the case of S3 standard. Okay, so now let's see how we can actually access our data sets stored on Amazon S3 from machine learning workloads. And let's do this with Amazon SageMaker first. So taking a look at this slide that I have shown previously, again, we can see that there are a lot of different stages, a lot of different moving parts involved in the ML lifecycle. And there might be situations where you or your team doesn't want to build everything from scratch or manage it, or even might be that you don't have the skills to do so. So in these cases, we have Amazon SageMaker, that is our fully managed machine learning service to help you throughout every stage of machine learning lifecycle. And it also includes fully managed interfaces to data on Amazon S3 that I will talk about shortly. Well, let's first recap quickly how a machine learning training job looks like on Amazon SageMaker. So when you file a GET request to start a training job with SageMaker, the following sequence of events will happen. So first, the machine learning compute instances that you have specified in your API call will be automatically provisioned and put behind a virtual private cloud if you have requested that. Then a container can be your own container or one of the pre-built containers with different frameworks that we have on Elastic Container Registry will be pulled down and spun up automatically on the compute instances. Later, also, your custom training script will be injected into the container and executed. And also, as I have mentioned previously, data sets on Amazon S3 might be made available for you to access directly from the container if you have requested that. Once the training job finishes, all the provisioned resources will be turned down automatically, and all the machine learning artifacts that you have produced during your training job, they will stored back to Amazon S3. So you end up only paying for what you have actually used throughout the training. So now let's talk about the SageMaker managed data loading options from S3 that we have here. So first of all, we have file mode. File mode, in this mode, you give SageMaker, for example, an S3 prefix or a list of different S3 objects in a so-called manifest file, and all this data will be automatically downloaded upfront to the local instance storage, and then your training script will be able to read this data locally. Of course, in this case, it provides you very familiar file system-based data access with POSIX interface and really fast random I/O. However, the downside of this is that your data set will be downloaded upfront, which can incur, in some cases, some startup delays, especially if your data set is large or is comprised of a large number of small files. Another consideration to have in mind is your data must fit into the local storage instance. And also, if you read data locally, there might be cases where your throughput will be dependent on the volume size of the EBS-backed instances or the instance type itself if you're using NVMe-backed instances. And now, file mode supports S3 Express one zone, which will allow you to significantly reduce the download phase if you choose this input mode. However, there is another option to access data from Amazon S3 with Sagemaker, that is fast file mode. In this mode, the data won't be downloaded upfront, but rather directly streamed from the S3 bucket as your training script demands it. Of course, here there will be no startup delay, so your jobs will kick off near instantaneously. And since you are streaming data directly from S3, you can enjoy the highly elastic throughput that it offers. Basically, what that means is you can consume your machine learning training samples as fast as your CPUs can read and preprocess data. Also, your data sets no longer have to fit into the local instance storage. And most importantly, there is absolutely no code change required in the training script. So basically, for the training script, it appears as if the data has already been downloaded locally. However, as we have discussed previously, if you are doing random reads, you might suffer from somewhat lower throughput. But again, with the support of S3 Express one zone in fast file mode as well, you will be able to alleviate this last point substantially. So in order to summarize, Sagemaker have two different options to access data from Amazon S3, file mode and fast file mode. Use file mode to automatically copy data upfront and then read it locally from the local instance storage. And how to do this, how to kick off a job with this input mode. If you are using Sagemaker SDK, that is really easy. So first you instantiate an object that is called estimator, which is nothing else than a collection of different configurations in order for Sagemaker to know how to execute the training job. For example, you specify the image URI of your container from the Elastic Container Registry. You point the estimator object to the custom training script, and then you specify the input mode, in this case file mode. You specify the inputs, in this case it is the S3 prefix, and then you kick off the training job by calling the fit function, and all of those chain of events that I have previously shown will be automatically executed. And use file mode if you would rather stream your data directly from S3 on demand as your training script reads it without any code change. Again, and what I mean by without code change, I mean that you literally only have to add 4 characters into the specification of the input mode in order to do so. So you can quickly jump from one read pattern to another read pattern to see what works best in your case. Of course, Sagemaker is just one of the many options that we have on AWS to do machine learning training. And here I will hand over to my colleague, James, in order to walk you through some other options that we have here.
Awesome. Thank you. Good morning. So how many people are here at re:Invent for the first time? Awesome. Me too. I hope you're having a great conference. Congratulations on making it to Wednesday. You're halfway there. I'm going to tell you a little bit about how some of the work we've been doing on making it easier to use S3 to train ML models using your own computes, or if you're not on Sagemaker. Now, one of the things that I've been finding really interesting about working in the AI/ML space recently is that things are changing really fast, right? And so rather than trying to tell you something about how to overfit for any particular model or algorithm or something like that, I thought what I would do with our time is tell you some general purpose answers, right? Things that we think will work well in any scenario. And then gradually we'll work towards a couple of more specialized solutions that will work in cases that you're likely to run into, but are specialized to particular use cases. One of our kind of guiding tenets for S3 is it should be simple to use. In fact, it's actually in the name. We don't say the name out loud very often, but S3 is simple storage service. We want it to be simple to use. And what we think about when we talk about clients then is it should be easy to get data in and out of your application from S3. We don't want you to have to think about the difficulties of getting storage in and out, how do you make it go fast, how to optimize it, all that kind of stuff. We want to do that work for you. The team really spends a pretty remarkable amount of time thinking about simplicity, thinking about how to make S3 easier and faster for you for free. And so I want to tell you a little bit about some of the work we've been doing in that space. One of the first things we did here earlier this year was the launch of a new product we called Mountpoint for Amazon S3. Mountpoint is what we call a file client. What that means is that it presents your S3 bucket, your objects, as if they were files in a local file system. And we built Mountpoint because we heard from customers that they really loved S3's low cost, its elasticity, but they had applications that either didn't understand S3's APIs, didn't speak object APIs, or didn't speak object APIs as fast or as high performance as they would want them to be. And so when we were looking at this feedback, what we realized was that actually there's already a pretty ubiquitous interface for getting data in and out of applications, right? It's the file interface. Every application for the last 50, 60, 70 years understands how to speak file, right? It's probably not something you think of as a feature in an application. Just file is the thing that it does. And so with Mountpoint, what we did was build a way for you to get your S3 objects through the file system with the same high performance, the same elasticity, the same low cost that you expect from S3's object APIs. What that means for ML training is that your Mountpoint is a really great default option for getting data in and out of your applications. Because just like every application understands files, every ML framework that you can think of has interfaces for getting data out of files for training, for loading training samples, and saving data back into files for model checkpoints and things like that. Mountpoint is super easy to get started with. After you install it, it's a one-line piece of code to sort of start up Mountpoint. You tell it what bucket you want to use, where you want to present it on the file system, and then you'll be able to get your objects through that interface. And all the code you can find on the internet for any ML framework will just work through the interface. So for example, if you're training a model, like a vision model using PyTorch, you can use the built-in image folder dataset abstraction to just load stuff out of an entire folder in your S3 bucket as if it was local. Same thing if you're working with TensorFlow, right? If you're using a TensorFlow training pipeline, you can use its built-in features for listing files and directories, opening files and directories to get data into your TensorFlow training from S3 through this file interface. And again, the really important thing here is that Mountpoint is going to give you really high performance when you're training against S3. So let me tell you a little bit about what that looks like. One of the things that makes Mountpoint awesome is that you get this performance out of the box. And so what I have here are some examples or some results comparing a Mountpoint-based training pipeline to one that uses FSspec. Now, you might not have heard of FSspec. It's a pretty common library for this kind of thing. If you're using an ML training framework and you're already getting data out of S3, it's kind of built in, you're probably using FSspec under the hood because most frameworks build it in. And so that's what we're going to compare to here. Now, as Alex was telling you earlier, one of the most important decisions you can make when designing an ML training pipeline on S3 is how you arrange and access your data. Right? There's a big difference between having one training sample per object, sort of random access files in your bucket, versus being able to combine many different objects many different samples into larger objects, and accessing them sequentially, reading them front to back. And so I'm showing you both those results here. Right? So on the x-axis here is training throughput. So higher is better. We want to see more images per second. We're training a pretty small vision model here. And what I'm showing you is results for both random and sequential access. So the first thing to notice is exactly what Alex was telling you, right? Being able to collocate your file or your samples into larger objects dramatically increases training throughput, right, by up to 10x in this case. So sequential is better if you can get there. The other thing I wanted to show you here is that Mountpoint is actually up to 60% faster than FSspec, especially in this large object case, right? Mountpoint has a bunch of optimizations built in that actually I'll tell you more about later that are really optimized for streaming large objects out of S3 at really high throughput. The other thing you might notice on the slide, by the way, if you're paying sort of close attention, is that actually in the random access case, Mountpoint's a little bit worse than FSspec. Don't worry, we're going to fix that in a couple of slides. But this is sort of the big point one should take away from this, right? Like Mountpoint is a great way to get good performance in an ML training pipeline, hopefully with very little work on your part. We're not done. We've actually launched 2 recent new features for Mountpoint that are going to make this even better for some of your training use cases. The first thing we launched last week is that Mountpoint can now cache training data locally on instance storage or on EBS volume. What that means is that we can further speed up your training jobs, especially jobs that are repeatedly accessing the same data. So if you're training for multiple epochs on the same data set, this caching is going to work great for you. Like everything else with Mountpoint, we want it to be really plug and play. And so really, it's just a one-line thing to do to turn on the cache. You just tell us where you want us to cache your data. That can be a file system on your local NVMe storage. It can be an EBS volume that you've mounted, or it can be even local memory if you set up a temporary disk. Now, of course, you could get the same performance benefit by just doing this yourself, right? You could download all the objects onto your local storage and then just read from them directly and not have to have Mountpoint or S3 in the loop at all. And that would totally work. right? But the difference here is that Mountpoint's going to do a lot of the heavy lifting for you, right? So if you don't want to read all the objects out of your S3 bucket, maybe you want a subset of them, Mountpoint will load them dynamically for you, so you don't have to think about, I only want this subset of my objects or that subset. Mountpoint's going to manage the cache for you, so if it doesn't fit in cache, we're going to do cache eviction and cache admission for you for free. So Mountpoint's going to do a lot of the heavy lifting that you would otherwise have to do if you were downloading your own objects onto local storage. So I promised you this would be faster, and actually in sort of simple benchmarks, it is up to 2.5 times faster when you read out of the cache, which makes sense, the storage is local. But let me tell you a little bit about how this works specifically for machine learning training. So this is the same benchmark I was showing you a few seconds ago, a pretty simple small vision model. Except this time I'm going to show you multiple training epochs. So the x-axis here is going to be the epochs, and the y-axis is going to be throughput. Now, as you saw earlier, without this feature, when we train on individual image files, so sort of random access to S3, throughput's not great, right? Because you're sort of bound by S3's latency in this case. But when we turn on the Mountpoint caching, we see a couple of interesting things. The first one is that even in the first epoch of this training, Mountpoint is faster with caching turned on. And that's a little bit weird, right? Because you're still downloading the objects from S3 in that first epoch. They're not on their local storage yet. What's going on is that Mountpoint's also able to cache metadata. Right, so this first epoch, this first iteration is faster, not because we already have the data, we're still downloading the data, but the metadata is cached the first time around. And so even the first epoch is faster. But then it's after the first epoch that things really kick into gear, right? And so as we get into these later epochs where we're serving all of your requests entirely from cache, not speaking to S3 at all, training's up to 2 times faster using this caching feature than going directly to S3 every time. So I'm really excited for you to try out this new caching feature of Mountpoint. It's a pretty plug-and-play way to get better performance from multiple epoch training on S3. The second new thing that we launched recently is something that actually Dev has already mentioned to you a couple of times, right? It's the new storage class for S3, Amazon S3 Express OneZone. S3 Express OneZone is our new high-performance storage class. It's built for single-digit millisecond latencies for your objects. Unlike most of our storage classes, S3 Express OneZone objects are stored in a single availability zone to minimize access latency, and that means that you can co-locate your compute closer to your storage to get even better performance. Amazon S3 Express OneZone also has a new kind of bucket, the first time we've ever launched a new bucket type for S3, called the directory bucket. This directory bucket is a thing that optimizes specifically for high request rates, for high parallel throughput, for high TPS. And so hopefully, given the kind of build-up that I've given you, it won't surprise you to learn that this week we also launched Mountpoint support for S3 Express OneZone. What that means is that you can just use Mountpoint like you were doing it before, except you can point it at a directory bucket instead of a regular bucket, and you'll get access to this low latency storage class through a file interface. And so what we've seen here again is up to 30% higher throughput training against S3 Express OneZone with individual files stored there versus stored in S3 standard. What I find really exciting about this actually is that it sort of starts solving this question of like having to make a decision about storage classes and storage files and layouts and that kind of stuff. You can just put individual image files in S3 Express OneZone, and you'll get pretty good training throughput out of it, right? So one of the goals here is to try to make it easier for you to have to make fewer decisions in your training pipeline. And so that's Mountpoint. Again, we think Mountpoint is really a great general purpose answer for getting data in and out of S3 in any training pipeline, anything that understands files, which is pretty much everything. Now, if you wanted to, you could leave right now, right? This is kind of the most important thing I wanted to tell you. Mountpoint is awesome, you should try Mountpoint. I hope you'll stay, because I have a couple more things to tell you about that I think are really cool, and I'm going to specialize for a couple of the most common scenarios you're going to run into in any ML training pipeline, getting data in and getting data out. And the S3 team has been working on some really cool stuff here, specifically for ML training. First, though, I hope you'll sort of geek out with me for a couple of slides about how clients like Mountpoint are able to get all this awesome performance out of S3. As you probably know, S3 has been the storage service of choice for data lake workloads for over a decade now. And along the way, we've learned a ton about how to get really high performance and really high elastic performance out of S3 at scale. A few years ago, we realized that there was really a need to bring some of our performance best practices, things that we tell customers to do with S3, to as many of our clients as we could. And so we built this really cool software stack that we call the AWS Common Runtime, the CRT. The Common Runtime is a collection of libraries that offer all the things that you need to interact with S3. Things like asynchronous I/O, a HTTP client, encryption, authentication, all that kind of stuff. Most importantly, it includes an S3 client. And that S3 client does a bunch of really smart things, like automatic request parallelization to do multi-part gets. Things like load balancing across different DNS servers, things like retries and timeouts, that sort of thing. All the things you need to build a high-performance, high-reliability S3 client. Let me give you an example of the kinds of things the CRT can do. One of the great things about S3 is its simplicity, right? It's just a HTTP service. You can upload to S3 or download from S3 from anything that speaks HTTP. When you do that, you're going to get about 100 megabytes a second speaking to a single S3 front-end host. But as you probably know, S3 is not just one server, right? S3 is actually a pretty massive collection of front-end servers. And so one of the things the common runtime knows how to do is fan out your requests across multiple S3 front-end servers to get even higher throughput, to aggregate throughput across all of these servers. This is also able to take advantage of some of our recent launches, things like multi-value answer DNS, to give you back more responses, more servers you can access more quickly. And so the S3 team has really been relentlessly looking for opportunities to use this common runtime, to use the CRT to transparently accelerate your applications. And it really comes back to that guiding tenet of simplicity that I was talking about, right? We really want S3 to be something that you don't have to think about, right? That it just works for your training workflows. And so we've been looking for opportunities to use the CRT for more things. One of the areas where we identified an opportunity like this is in training workflows that use Kubernetes to orchestrate their training jobs. Often these are distributed training jobs across multiple nodes. Now, there are a few different ways that customers orchestrate training jobs like this today. But what we've heard pretty often is that customers want to use the Kubernetes primitives that they're familiar with from their other production workloads to orchestrate ML training as well. Often they also want to use EKS, our managed Kubernetes offering, to sort of do the configuration, the automation for them. Now, what makes Kubernetes really cool is that it's a declarative way to manage training infrastructure, right? You launch your training jobs, you declare what resources they access, and you can scale them up and down as you need without manually managing individual nodes or the connections between them. And so if you're using Kubernetes or EKS to manage your training jobs, this week we launched the new Mountpoint CSI driver for Kubernetes. The Mountpoint CSI driver makes it really easy to attach S3 storage to your Kubernetes pods. And it's just Mountpoint under the hood, as the name suggests. So you declare that you want to mount a particular S3 bucket to your Kubernetes pod, and it shows up like the Mountpoint I was showing you before. It shows up as a directory in your pod that you can access through a file interface. And you get the same great performance that we were talking about for the Mountpoint before, right? The high throughput access to S3. If you're using EKS, the Mountpoint CSI driver is also available as an EKS add-on. What that means is that you can use EKS and let EKS manage deploying this add-on to your cluster automatically. So you don't have to do the work of deploying it yourself. So we're really excited about this for customers who are using Kubernetes in particular to manage their training workflows. Again, we think it's a really great default option to get S3 data in and out of your containerized applications without any heavy lifting on your part. Let's talk a little now about frameworks and the frameworks that you use for ML training. There's really a plethora of options here. There's tons of options for ML training. Probably some grad student right now is writing a new framework as we speak. But mostly what we hear from customers is they're kind of focusing on PyTorch, right? PyTorch is increasingly a framework of choice for training ML models. And this makes a bunch of sense, right? PyTorch has all the primitives that you need to support all kinds of models, all kinds of training algorithms. It has many different training accelerators supported, things like GPUs and Trainium chips. It's also the language of choice for a lot of research these days in ML. And so even though we think Mountpoint is a really great default option for getting ML data in and out of any training workflow, we think in the case of PyTorch, there's some opportunities where we can do even better, specifically for PyTorch access. So I want to tell you a little bit about that. Last week, we launched the new Amazon S3 connector for PyTorch. The connector for PyTorch closely integrates S3 with your PyTorch training pipelines. Now, unlike Mountpoint, using the S3 connector for PyTorch requires a little bit of code change on your part, right? You have to use it in your training code. But in return, it's going to help you solve two of the most important problems in any ML training pipeline: how to get training data into the pipeline, and then how to get model checkpoints out of the pipeline. I'm going to talk about each of those in turn. But the common theme here is going to be that by using the AWS common runtime, the S3 connector for PyTorch makes it really easy to get that elastic performance that we were talking about before to reduce your training time and costs. So let's start by talking about data loading. What we heard from customers using S3 for training data is that there's a lot of boilerplate work they have to do to get data in and out of their training workflows. So for example, if you want to stream data out of S3, rather than loading it all up front, today you're on the hook for managing all of that. You have to go and list your bucket. You have to go and manage gets, often parallel gets to multiple different objects. You have to interleave those if you want to get really good streaming performance. There's a lot of work that you have to do to make this work. On the other hand, if you want random access to your training set, right? If you want to be able to sort of randomly access individual samples, again, you're on the hook for managing this, right? You have to go and list your bucket, figure out how to map indexes to objects, and maintain that listing consistently, often across many different training nodes. And so to make these problems simpler, the S3 connector for PyTorch has two abstractions for loading data directly from S3. In the streaming case, it has what we call an S3 iterable dataset, an iterator-style dataset for PyTorch. This is going to stream objects from an entire prefix of your S3 bucket. And it's a one-line piece of code, that's going to do all the work that I just talked about. It's going to manage listing your bucket for you. It's going to interleave those listings with gets so we can get high throughput out of S3. It's going to do all the work of streaming objects out of your S3 bucket. On the other hand, if you want random access to your S3 bucket, we also provide a map style data set. This is something where you can sort of look up objects in your bucket by random access. And again, it's going to do all the work for you, right? So you tell us what prefix your training data is saved in, and then it will do all the work of listing your bucket, figuring out how to map indexes back to objects in your bucket, and again, doing those gets for you with high performance. The cool thing about both these data sets is they integrate tightly with PyTorch's existing data loader infrastructure. So these will just work if you're already using PyTorch for data loading. And what we've seen, again, comparing to FSspec before, with the iterable style data set in particular, what we've seen is up to 50% higher training throughput using these data loaders, using these data sets, rather than using the built-in FSspec libraries. So that's the data loading side. Let's talk a little bit about checkpointing. For large-scale training, and especially for distributed training across hundreds of nodes, it's really important for your training jobs to periodically save checkpoints in the model state, so that if one of those nodes fails, you don't have to go back to the beginning and start again. Now, checkpointing in most ML training algorithms these days is a stop-the-world operation, right? All the nodes need to stop, pull their state off the GPU, save it to storage, and no one can start training again until all those saves have happened. What that means is that checkpointing performance actually directly affects the training time and cost of your training jobs. It also means that checkpointing is a really bursty and really demanding storage operation, right? You might only save a checkpoint once every hour, but when you're saving that checkpoint, you need the storage to be as fast as possible, right? Because every second that you spend saving that checkpoint is a second you don't spend doing useful work in your training pipeline. This is a really great fit for S3, right? S3's elastic performance means you can burst up to potentially hundreds of gigabytes per second of throughput when you need it to save a checkpoint, and then scale back down to 0 immediately and only pay for what you used. And so we think S3 is a really great target for saving checkpoints. And so part of the S3 connector for PyTorch is an interface for saving checkpoints and loading checkpoints directly to and from S3. Again, it's a couple of lines of code that plug into PyTorch's native checkpoint saving and loading framework. But you can just say, I want to save this checkpoint to this path in my S3 bucket, and we'll take care of streaming the object for you as quickly as possible using the CRT. What's awesome about this is it's really high performance. It's certainly much faster than other S3 clients we've tested. But the really surprising thing here is that actually we also found that it's up to 40% faster to save a checkpoint this way than to save a checkpoint to local NVMe instance storage. Now, if you're like me, you hear that number and you say, that's ridiculous. That can't be true. Like, how is that possible? NVMe is really, really fast. And the answer is, well, like, yeah, NVMe is really, really fast, right? That's definitely true. But remember this picture that I was showing you before, right? One of the benefits of the common runtime on which we built the connector for PyTorch is that it makes it really easy to burst your object uploads across the entire S3 fleet. So when you're going to save one of these checkpoints, rather than saving it to a single NVMe disk on your instance, you actually get access to the entire scale of S3, right? Potentially millions of storage devices to save your checkpoint to at once when you need it, and then scale back down to 0 once you're done. So we think this is a really great way to handle model checkpointing that will reduce your training costs, increase your training throughput, and increase your flexibility to retain your model checkpoints in S3, to use our storage management features, things like intelligent tiering, to manage your checkpoints for you. Now, like everything I've mentioned today so far, the Amazon S3 connector for PyTorch is an open source product. So we're really excited to hear your feedback on it, contributions for it particularly, if you're interested in doing that. And the team is really just getting started here. But this is our first step in sort of more tightly integrating PyTorch and S3 together to make it a really great training experience when you're using training data stored in S3. The last thing I want to tell you a little bit about is to admit that even though we're really excited about Mountpoint and the Mountpoint CSI driver and the S3 connector for PyTorch, we also recognize that they're not going to solve every problem for you, right? Sometimes you're just going to have bespoke data loading needs. Maybe your bucket is laid out in a certain way, or you want to build your own prefetching logic because you know better, or there's some other reason that you just can't use these off-the-shelf tools. In these situations today, you'd probably use Boto 3, the AWS SDK for Python, or maybe you use the CLI, right, to get your S3 objects in and out of S3 onto local storage or into your application in the Boto's case as fast as you can. And when you use the Boto 3 or the CLI, we want you to get the same great S3 performance that we've been showing you so far through Mountpoint and the S3 connector. And so this week we announced also that AWS Common Runtime is now enabled by default for S3 transfers in Boto 3 and the CLI when running on ML training instances. That's P4D, P5, and TRN1. It's also available as an opt-in on any other instance type. What that means is that you can now get access to the same CRT-based throughput that I've been showing you from your applications directly, even if you're not using one of our higher-level tools. For example, if you're uploading or downloading ML checkpoints or ML training data, we've seen up to 3 times faster downloads using the CLI with this new CRT integration than we saw without it. Up to 5 times faster uploads using the CLI with the CRT integration. So if you're not able to use one of our higher level tools, starting this week, Boto 3 and the CLI can now do a lot of this heavy lifting for you, and hopefully it'll be much faster. And so I encourage you to try those out as well. And so that's pretty much all I wanted to share with you. Again, sort of 3 key takeaways, I think, to take away from this session. The first and the most important one by far is what Alex was telling you about data access patterns. It's the most important decision you can make when training on S3. Think about sequential versus random. Can you combine multiple samples together into larger objects, or do you have to do random access? If you have to do random access, think about whether you can use S3 Standard or S3 Express One Zone, our new low latency storage class, to reduce the cost of those random accesses. The second thing I think is really important is to be on SageMaker if you can. Right? SageMaker is awesome, and it does all this work for you. Right? You don't have to think about, other than making that choice between file mode and fast file mode, you don't have to think about how to optimize all this training throughput for you. We'll do all the work for you there. If you're not on SageMaker, then our general purpose advice here is use Mountpoint. Right? That should be the first thing you try. It will work really well in many cases. It works in pretty much any training framework that you can think of, and it gives great performance. The S3 connector for PyTorch is also a great option if you're in PyTorch, specifically if you're training large models or you're saving large model checkpoints. The S3 connector for PyTorch is a great place to be. There's some really great storage training materials we have available if you're interested in learning more about how to use S3 or any of our storage services. And with that, I just want to say thank you very much for being here. The 3 of us will be outside those doors. If you want to have questions or want to talk about S3 or anything like that, we're also happy to talk over email if you have other questions. Other than that, thanks for being here this morning, and have a great re:Invent.